The cosmos holds secrets that defy our understanding. We are about to journey through 25 of the most baffling, unsolved mysteries in the universe. This is a deep dive into the cosmic puzzles that keep the world's greatest scientists awake at night, from invisible forces shaping reality to signals that might just be whispers from another world. By the end, you will see the universe not as a static map, but as a living, breathing enigma. We will confront a force that is tearing space itself apart and an object that entered our solar system from the void between stars. Which cosmic mystery do you think challenges our place in reality the most? Our first stop is a question so profound it has echoed for generations. It is known as the Fermi Paradox, named for the brilliant physicist Enrico Fermi. During a casual lunch conversation in 1950, Fermi posed a simple, devastating question. Given the vast number of stars in our galaxy, many with planets, and the immense age of the universe, where is everybody? The math seems to scream that we should not be alone. The Milky Way alone contains hundreds of billions of stars. If even a tiny fraction hosts life and a fraction of those develop intelligence, the galaxy should be teeming with civilizations. We should see their ships, hear their signals, or find some trace of their existence. Yet we see nothing but an immense silent void. This is the paradox, the great silence that stands in stark opposition to our cosmic optimism. To frame this puzzle, scientists use a tool called the Drake equation. It is not a hard calculation, but a way to think about all the factors needed for a communicating civilization to arise. The equation multiplies things like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually begins, the fraction where life becomes intelligent, the fraction that develops technology to broadcast signals, and finally, the length of time such a civilization lasts. Plug in hopeful numbers and you get a galaxy full of neighbors, but our reality so far suggests one or more of those factors is tragically small. This leads us to the chilling idea of the Great Filter. This hypothesis suggests there is at least one enormous, perhaps insurmountable, barrier that prevents life from advancing to the stage of interstellar colonization. The terrifying question is, where is this filter located? Is it behind us, meaning the step from simple chemistry to life, or from single cells to complex intelligence, is miraculously rare? If so, we are incredibly lucky to be here, or worse, is the filter still ahead of us? Could it be that every advanced civilization eventually destroys itself through war, environmental collapse, or some technology we have not yet invented? The silence of the cosmos might then be a warning. Other solutions are less grim, but equally mind-bending. Perhaps we are simply too primitive to notice the conversation happening all around us, like ants unaware of the internet. Or consider the zoo hypothesis, which proposes that advanced civilizations are aware of us, but have chosen to place Earth in a kind of cosmic quarantine, observing us from a distance until we reach a certain maturity. They are letting us grow, or perhaps they are waiting to see if we destroy ourselves first. Every silent radio telescope scan, every empty patch of space, whispers these possibilities. The answer to the Fermi Paradox will fundamentally reshape our understanding of reality, telling us either that we are precious and alone, or that we are newcomers in a crowded and very quiet neighborhood. This silence points directly to the most unsettling answer to the Fermi Paradox, a concept known as the Great Filter. It proposes a single, nearly insurmountable barrier, a wall in the evolutionary path that almost every species hits and cannot get past. The sheer emptiness of the cosmos suggests this filter is incredibly effective, wiping out civilizations before they can fill the galaxy. The crucial and terrifying question for us is one of timing. Is the Great Filter behind us, or does it still lie ahead? If it is behind us, we are the beneficiaries of a cosmic miracle. It means the step from non-living chemistry to the first self-replicating cell, or the leap from simple single-celled life to complex, intelligent beings, is so astronomically rare that it has almost never happened before. In this scenario, we have already won the universe's greatest lottery. Our existence itself is the answer to the silence. We are the first, or among the very few, to have made it this far. The galaxy is empty because we are the pioneers, but the alternative is far darker. What if the filter is still in our future? This is the possibility that haunts every scientist who contemplates it. It suggests the true test is not becoming intelligent, But surviving that intelligence, the most common candidate for a future filter is self-annihilation. Perhaps every civilization, upon reaching a certain technological level, inevitably creates the means of its own destruction, whether through nuclear war, engineered pandemics, runaway artificial intelligence, or ecological collapse. The silence would then be a graveyard of species who reached our stage and then vanished. This gives our search for other life a morbid new dimension. We are not just listening for hello, we are searching for obituaries. If we found definitive evidence of a single, long-dead alien civilization, even just ruins on a distant world, it would be simultaneously the greatest discovery in history and the worst news we could receive. It would strongly suggest the great filter is not behind us but ahead, waiting for us to stumble into it. That discovery would tell us that intelligence is not rare, but longevity is. For humanity, this is not just an abstract puzzle, it is an existential warning system. Every global challenge we face, from climate change to the risks of advanced technology, could be a potential component of that filter. Solving these problems is not just about improving life on Earth, it is about proving that a technological civilization can reach maturity without self-destructing. We are, in a very real sense, running an experiment with the highest possible stakes. The outcome will determine whether we become a silent data point in the cosmic statistics, or whether we finally, truly, answer Fermi's question by stepping out into a galaxy that is waiting for us to speak. The silence of the cosmos is not its only ghost. While we search for signs of other life, a far more tangible, yet utterly invisible, presence shapes the universe itself. This is the mystery of dark matter. It is a substance that makes up roughly 27% of everything that exists, yet it refuses to interact with light. We cannot see it, touch it, or detect it with any conventional telescope. We know it is there only because of its immense gravitational pull, a ghostly hand gripping the cosmos. The evidence first appeared in the motion of galaxies. When astronomers measured how fast stars orbit the center of their galaxies, they found something shocking. The stars on the outer edges were moving far too quickly. According to the laws of gravity and the amount of visible matter we can see, those distant stars should have been flung out into the void. The fact that they are not tells us there is something else there, a huge amount of unseen mass providing the extra gravity to hold the galaxy together. Think of it like watching a playground merry-go-round spinning at a dangerous speed. The children clinging to the outer edge should be thrown off, but they are not. You would logically conclude there must be some invisible force, some unseen harness holding them in place. That harness is dark matter. Its influence extends far beyond single galaxies. When we look at massive clusters of galaxies, we see their gravity bending the light from objects behind them, a phenomenon called gravitational lensing. The amount of bending is so extreme that it requires 6 times more mass than all the visible stars, gas and dust combined. This invisible mass forms a vast, intricate scaffold known as the cosmic web, a skeleton upon which the luminous galaxies are draped like glitter on a dark tapestry. So what could this ghostly substance be? The leading idea points to an entirely new class of particle, one that barely interacts with the ordinary matter that makes up you, me, and the stars. Scientists call these candidates WIMPs, which stands for weakly interacting massive particles. True to their name, they would have mass and field gravity, but they would pass through normal matter almost like a ghost walks through a wall. Another promising candidate is the action, a theoretical particle that is extremely light, but could exist in such staggering numbers that it adds up to the missing mass. The hunt for these particles is one of the most challenging experiments in human history. Because they interact so weakly, detecting one requires shielding from all the cosmic noise of the universe. Laboratories are built deep underground in old mines or beneath mountains to block out other particles. There, scientists maintain ultra-sensitive detectors, waiting in the profound silence for the almost impossible event, a single dark matter particle bumping into an atom of normal matter. They have been waiting for decades, and so far the detectors remain quiet. This only deepens the mystery. We are surrounded by an ocean of something we know is real, something that dictates the fate of galaxies and the large-scale structure of everything we see, yet it remains forever just out of reach. It is the universe's most dominant material, and we are utterly blind to it. But if dark matter is the ghostly anchor holding the cosmos together, there is another, even more dominant phantom at work, one that is doing the exact opposite. This is the enigma of dark energy, and it makes up a staggering 68% of the entire universe. While dark matter pulls with gravity, dark energy pushes. It is a repulsive force woven into the fabric of space itself, and it is causing the expansion of the universe to accelerate, not slow down. This discovery shattered a fundamental assumption. For most of the 20th century, scientists believed the universe's expansion, born from the Big Bang, was gradually slowing due to the collective gravity of all matter pulling everything back together. The big question was whether that gravity would one day win, leading to a big crunch, or if the expansion would simply coast to a halt. Then in the late 1990s, two independent teams of astronomers made a measurement that turned cosmology upside down. They were observing a specific type of stellar explosion called a Type 1, a supernova. These events are cosmic standard candles, meaning they always explode with the same intrinsic brightness. By measuring how dim they appear from Earth, astronomers can calculate their distance with incredible precision, and by examining the color of their light stretched by the expansion of space, they can determine how fast the universe was expanding when that light was emitted billions of years ago. The results were unequivocal and shocking. The most distant supernovae were fainter than they should have been. This meant the universe is expanding faster today than it was in the distant past. The expansion is not slowing down, it is speeding up. Some unknown force is overpowering gravity on the largest scales. That force is what we call dark energy. The leading explanation reaches back to an idea Albert Einstein once proposed and then discarded: the cosmological constant. This is the energy inherent to empty space itself. According to quantum physics, a vacuum is not truly empty, but a seething foam of virtual particles popping in and out of existence. This quantum froth should imbue every cubic centimeter of space with a tiny amount of energy, and that energy would have a repulsive gravitational effect. This fits the role of dark energy perfectly, but there is a catastrophic problem, a discrepancy so vast it is often called the worst theoretical prediction in the history of physics. When physicists calculate how much energy this quantum vacuum should have, the number they get is about 120 orders of magnitude too large. That is a 1 followed by 120 zeros. If that predicted value were correct, the repulsive force would have been so unimaginably powerful that it would have ripped atoms apart before they could even form. No stars, no planets, no life would ever have been possible. Clearly, the real value of dark energy is almost zero, but not quite zero, and we have no idea why. It is as if the universe is balanced on a knife's edge, and we cannot explain the precision of that balance. Dark energy is now the dominant component of our cosmos, and its influence is only growing. As the universe expands, more space is created, which means more dark energy. This leads to a profoundly lonely future. If this acceleration continues unchecked, billions of years from now, distant galaxies will be pushed away faster than the speed of light, vanishing from our view forever. The observable universe will shrink to our immediate galactic neighborhood, leaving our descendants with a night sky devoid of any external galaxies, a silent island universe. We are left with a cosmos where 95% of its content is completely invisible, a partnership of shadows where one ghost holds structures together while the other relentlessly drives them apart. Our galaxy is not drifting aimlessly through the void. It is on a collision course, pulled by a force so immense it defies the very expansion, driven by dark energy. This is the mystery of the Great Attractor, a gravitational anomaly of almost incomprehensible scale. Our Milky Way, along with our entire local group of galaxies and thousands of others, is being dragged toward a specific point in space at a velocity of over 1 million miles per hour. We are a cosmic river caught in a current we cannot see. The destination lies in the direction of the constellations Centaurus and Norma, but for a long time, its true nature was hidden from us by a cosmic curtain. This region sits directly behind the dense plane of our own galaxy, an area so packed with gas, dust, and stars that it is known to astronomers as the zone of avoidance. It is like trying to see a distant city through a thick, blinding fog. For decades, this zone blocked our optical view, leaving the Great Attractor as little more than a troubling anomaly in the data. The first clues came not from seeing the attractor itself, but from observing the strange motions of everything around us by carefully measuring the redshift of galaxies, which tells us how fast they are moving away from us due to the universe's expansion. Astronomers noticed something was off. The galaxies in one vast hemisphere of the sky were all showing peculiar velocities, their motions deviating from the smooth Hubble flow. They were streaming en masse toward the hidden center of this gravitational pull. It was as if we were standing in a valley and noticing all the rivers were flowing in one direction, pointing toward a hidden mountain range we could not yet see. To pierce the veil of the zone of avoidance, scientists turned to telescopes that see in wavelengths invisible to our eyes. X-ray observatories revealed massive clusters of galaxies hidden behind the dust, their hot gas glowing fiercely. Infrared telescopes, which can peer through obscuring material, began to map the structures. What they found was not a single, unimaginably dense object, but a colossal concentration of mass known as the Norma cluster, embedded within an even larger supercluster, now called the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is our true cosmic address. It is a web of 100,000 galaxies spanning over 500 million light years, and the Great Attractor appears to be its gravitational center of mass, a vast overdensity pulling everything in its local universe toward it. Yet the story may be even larger. The pull of the Great Attractor alone does not fully account for our motion. There seems to be something beyond it, an even more massive structure whimsically called the Shapley Attractor, exerting its own pull on us and on the Great Attractor itself. We are caught in a cosmic tug of war between the expansion of the universe and the relentless grip of gravity from structures so large they bend the paths of galaxies. Maps of these galactic flows look like wind patterns on a planetary scale, with elegant streams converging on hidden basins of gravity. So while the Great Attractor may not be a single exotic monster, its revelation taught us a profound lesson about our place in the cosmos. We are not isolated. We are part of a vast, dynamic architecture, riding gravitational rivers toward destinations we are only beginning to map, forever pulled by the hidden geography of the universe. That immense pull of gravity shapes galaxies, but what if something within them is trying to speak? In August of 1977, a radio telescope known as the Big Ear, quietly listening to the cosmos from Ohio, recorded something that has never been repeated. For 72 seconds, a powerful, narrowband radio signal blazed into its receiver. It was not static or the crackle of a distant star. This signal was concentrated on one specific frequency, the hydrogen line, which many scientists consider a logical channel for interstellar communication. When volunteer astronomer Jerry Amon reviewed the computer printout days later, he saw a string of letters and numbers representing the signal's intensity. The sequence was so startlingly strong that he circled it in red pen and wrote a single powerful word in the margin. Wow, that annotation gave the signal its immortal name. The WOW signal possessed all the hallmarks of a potential artificial broadcast. It was narrow, meaning it occupied a very slim slice of the radio spectrum, unlike the broad noise emitted by natural cosmic objects. It appeared and then vanished, suggesting the telescope's fixed gaze had passed over a localized source, and its frequency, 1,420 MHz, is protected by international agreement, a quiet band where earthly transmitters are forbidden, making radio interference unlikely. For that brief window, it seemed the universe had finally said hello. In the decades since, the search for a repeat has been frantic and utterly fruitless. Astronomers have pointed countless telescopes, including the mighty Very Large Array, back toward that patch of sky in the constellation Sagittarius. They have scanned for a follow-up signal, for a pattern, for any whisper of confirmation. The silence has been absolute. The signal's one and only appearance has fueled both hope and skepticism, leading to a quest for a natural explanation. One prominent theory suggested it could have been caused by hydrogen clouds surrounding a passing comet. The idea gained traction when researchers noted that two comets, undiscovered in 1977, were in roughly the same area of the sky at that time. Their hydrogen envelopes could, in theory, emit a similar signal, but this hypothesis has been heavily contested. Detailed analysis show the comets were likely not in the precise beam of the telescope, and more importantly, comets do not typically produce such a focused, narrowband burst. The debate remains unresolved, leaving the WOW signal in a tantalizing limbo. To this day, it stands alone. It is the single best candidate for a potential extraterrestrial signal in the history of the search for extraterrestrial intelligence, or SETI. You can even hear its ghost, a representation of its intensity converted into sound. Audio plays a tone that rises and then falls, a simple, haunting chirp. That sound is a question mark echoing across 45 years. Was it a cosmic mirage, a bizarre natural event we still do not understand, or a fleeting moment of contact from a civilization that broadcast once and then went silent? Its mystery endures precisely because it was never explained, a perfect solitary spike of curiosity in the endless noise of space. While the wow signal was a solitary question, the cosmos has since revealed a phenomenon that asks the same question over and over, in a furious cosmic stutter. These are fast radio bursts, or FRBs, and they are among the most violent and mysterious events ever detected. Imagine the sun releasing more energy in a single millisecond than it does in 80 years. Now pack that unimaginable power into a flash of radio waves so brief it could be missed in a blink, and launch it across billions of light years of space. That is the scale of an FRB for a thousandth of a second. A source out there screams in the radio spectrum and then vanishes. The first one was not even seen in real time. It was found in 2007, buried in archive data from the Parkes Radio Telescope in Australia, a 6-year-old blip that astronomers had initially dismissed as terrestrial interference. Once they recognized it for what it was, a genuine signal from deep space, the hunt was on. Today, with advanced instruments like Canada's CHIME telescope, which scans the entire northern sky daily, we are detecting them all the time. Dozens, sometimes hundreds of these bursts are now cataloged, turning a rare curiosity into a daily cosmic event. So what could possibly create such a brief, catastrophic flash? The leading suspect is a type of stellar corpse called a magnetar. A magnetar is a neutron star, the collapsed core of a massive star, but with a magnetic field so intense it defies comprehension. It is a quadrillion times stronger than Earth's field. If a magnetar were halfway between Earth and the Moon, it would erase the data on every credit card on the planet. Theorists suggest that starquakes on the surface of these monsters, or sudden magnetic field reconnections, could unleash titanic bursts of energy that we see as FRBs. This theory gained incredible support in 2020 when an extremely bright radio burst was detected coming from a known magnetar within our own Milky Way galaxy. It was the smoking gun, proving that at least some of these bursts are born from these magnetic dynamos, but the mystery is far from solved because some FRBs repeat. They are not one-off explosions. They flash, go silent for days or months, and then flash again from the exact same point in the sky. This rules out cataclysmic, self-destroying events like colliding neutron stars. A repeating source must survive its own outburst. This has led to more speculative, thrilling ideas. Could they be produced by beams from advanced alien spacecraft, using unimaginable power to propel starships across the galaxy? While possible, scientists urge caution, as nature often proves more creative than our fiction. The true power of FRBs may not just be in their source, but in their journey. As these bursts travel across the universe, they pass through clouds of diffuse gas and plasma. This material slows different radio frequencies by tiny, measurable amounts. By analyzing this dispersion, astronomers can use each burst as a cosmic probe, weighing all the invisible matter it passed through on its way to us. Each millisecond flash is a lighthouse beam, illuminating the dark, tenuous material between galaxies, helping us map the universe's missing scaffolding. So we are left with a paradox of power and brevity. These are the universe's most energetic radio events, capable of being seen from other galaxies, yet they are over before you can snap your fingers. Some are solitary explosions, while others are persistent, repeating enigmas. They could be the death cries of exotic stars, the birth pangs of new physics, or perhaps something else entirely. Every new detection is another piece of a puzzle we are only starting to assemble, a staccato code broadcast from the dark. The universe speaks in whispers, but sometimes the quietest signals are the hardest to explain. Far beyond the orbits of the planets, two robotic pioneers were sending back a faint, persistent puzzle. The Pioneer 10 and Pioneer 11 spacecraft, after their historic missions to Jupiter and Saturn, were coasting into the dark, becoming humanity's first emissaries to interstellar space. Yet as they drifted farther from the sun, tracking their precise position revealed something deeply unsettling. They were slowing down, not by much, just a tiny, almost imperceptible amount, equivalent to a 10 billionth of the gravity you feel standing on Earth. But over years and billions of miles, this anomalous acceleration added up, pulling the spacecraft about 240,000 miles off their predicted courses. It was as if an invisible hand was gently tugging them back toward the inner solar system. For decades, this pioneer anomaly represented a ghost in the machine of celestial mechanics. The laws of gravity, as described by Einstein and Newton, had predicted their paths with incredible precision, accounting for every planet's pull and the pressure of sunlight itself. Yet here was a discrepancy that refused to vanish. Was it some unknown drag from interplanetary dust? Could it be a subtle flaw in our understanding of gravity itself, a hint that Einstein's theory needed modification at the vast scales of the solar system? The anomaly fueled speculation about new physics, even the influence of dark matter. It was a constant, tiny thorn in the side of cosmology, a reminder that our most trusted maps might still have uncharted corners. The solution, when it finally came, was a masterpiece of forensic engineering and a lesson in humility. The culprit was not a cosmic force, but the spacecraft themselves. Both pioneers were powered by radioactive thermoelectric generators, which produced heat as a byproduct of generating electricity. That heat had to go somewhere. Scientists meticulously reconstructed the spacecraft's thermal blueprints, modeling how this heat radiated away into space. They discovered the answer was not perfectly symmetrical. More heat was radiating from the back of the spacecraft's dish antennae than from the front. This tiny imbalance acted like a minuscule photon thruster. Just as light exerts pressure, the infrared photons carrying heat away from the craft gave it a tiny, continuous push back toward the sun. It was the spacecraft in their final silent journey, pushing themselves off course. This mundane explanation solved the mystery, but its legacy is profound. The decades-long hunt for the anomaly's source drove unprecedented advances in deep space navigation and data analysis. It proved that to test the fundamental laws of the universe, you must account for every possible variable, right down to the warmth of the machine itself. And even solved, the story did not end. The meticulous methods developed to chase the pioneer anomaly are now tools for hunting far greater game. They provide a baseline of incredible precision, a way to see if any future deviation in a distant probe's path might be the real signal of new physics. So while the ghost was just a trick of the light, the search for it sharpened our vision, teaching us to listen ever more carefully to the faintest whispers from the dark. Our maps of the solar system end with a blank space and a question mark. Far beyond the orbit of Neptune, in the cold, sunless realm, lies a vast reservoir of icy worlds known as the Kuiper Belt. This is the solar system's attic, a frozen archive holding clues to our planetary origins. For decades, astronomers expected this belt to be a smoothly fading frontier. As you move farther from the sun, the number of objects should gradually thin out like a crowd dispersing from a city center. But the reality, revealed by painstaking surveys, is nothing like that gentle fade. Instead, the Kuiper Belt ends with a startling, sharp edge, a cosmic cliff, around 50 astronomical units from the sun, which is 50 times the distance from Earth to the sun. The population of these icy bodies doesn't just dwindle. It plummets. It is as if you were walking along a beach where the sand simply stops, giving way to an empty ocean. This sudden boundary is known as the Kuiper Cliff. Our models of how the solar system formed cannot easily explain it. In the primordial disk of gas and dust that surrounded our infant sun, material should have been distributed more or less smoothly. When planets like Neptune formed and migrated outward, their gravity should have scattered icy objects into a broad, diffuse cloud that gets steadily sparser with distance. The sharp cutoff we see defies that expectation. Something, it seems, swept this ridge and cleaned or prevented objects from forming there in the first place. One of the most compelling theories points to a hidden architect, a ghost planet. This is not the hypothesized Planet 9, a potential giant world much farther out, but another unseen world closer to the cliff. Astronomers suggest an Earth-sized planet, perhaps 2 or 3 times the mass of our own world, could be orbiting just beyond the cliff's edge, around 60 astronomical units out. The gravitational influence of such a planet would act like a cosmic shepherd. Over billions of years, its steady pull could have cleared out the region, either ejecting smaller objects inward toward the sun or flinging them out into deep space, carving that abrupt edge we see today. Finding this potential planet, dubbed Planet 10 by some, is a monumental challenge. It would be incredibly faint, receiving only a whisper of sunlight, and its slow orbital motion would make it blend in with the background stars. Another possibility looks back in time to the solar system's violent infancy. Perhaps the primordial disk of material itself had a sharp outer edge, cut off by the gravitational influence of a passing star in our sun's birth cluster, or simply because the cloud of gas from which the sun formed was finite. In this scenario, the Kuiper Cliff is a fossilized boundary, a permanent scar from the moment of our solar system's birth. It marks the outer limit of the construction zone. There simply was never much material beyond that point to begin with. Each theory has its own profound implications. A hidden Earth-sized planet would redefine our solar system's architecture, adding a major world we never knew was there. A fossilized edge would provide a unique snapshot of our sun's earliest environment. The Kuiper Cliff stands as a silent sentinel at the edge of the known, a stark reminder that even in our own celestial backyard, the map is not yet complete. The blank space beyond it beckons, holding secrets about what or who might be waiting in the dark. The sharp edge of our solar system is a puzzle of emptiness, but deeper in the cosmos, astronomers found a galaxy that was missing something even more fundamental. It appears to be a galaxy without dark matter. This discovery, centered on a faint, ghostly galaxy called NGC 1052 DF2, sent shockwaves through the world of astronomy. For decades, the standard model of cosmology was built on a simple, elegant idea. Dark matter forms first, creating vast, invisible halos. The gravity of these halos then draws in normal gas, which cools, condenses, and eventually forms stars, giving birth to the luminous galaxies we see. In this story, dark matter is not just an ingredient, it is the essential foundation, the skeleton upon which every galaxy is built. A galaxy without dark matter should be an impossibility, a cosmic contradiction. Yet the measurements of NGC 1052 DF2 were unequivocal. Astronomers studied the motions of its star clusters, those dense knots of stars that orbit a galaxy's core. The speed of these clusters reveals the galaxy's total mass, much like the orbital speed of planets tells us the mass of the sun. In a typical galaxy, the stars move so quickly that the visible matter alone cannot hold them in, proving the presence of a dominant dark matter halo. But in this strange galaxy, the star clusters were moving slowly, lazily. Their velocities perfectly matched the amount of mass calculated from all the visible stars alone. There was no extra mass, no hidden halo of dark matter. It was as if you found a massive spinning carnival ride operating with a tiny, visible motor and no hidden supports, defying all engineering principles. The immediate reaction was profound skepticism. Could the measurements be wrong? Perhaps the galaxy is oriented in a tricky way, fooling our calculations. Or maybe the dark matter is there, but it is perfectly aligned with the stars, a scenario considered highly unlikely. The debate raged, with teams reanalyzing the data, searching for any error. Subsequent studies of other similar ghostly galaxies, called ultra-diffuse galaxies, found a few more candidates that also seemed deficient in dark matter. This strengthened the case that the phenomenon might be real. If these galaxies truly lack dark matter, the question becomes how. One compelling theory involves a violent cosmic theft. NGC 1052 DF2 lies near a massive elliptical galaxy. Perhaps billions of years ago, it was a normal dwarf galaxy with its own dark matter halo. As it passed too close to its gigantic neighbor, the immense tidal forces could have ripped away both its dark matter and most of its gas, leaving behind a skeleton of stars, a galaxy ghost that had been stripped clean. Another more radical idea suggests these objects are not primordial galaxies at all, but tidal dwarf galaxies. They could have formed from the gas and stars ripped out during a colossal collision between two larger galaxies. Since this material comes from the gas-rich disks of the parent galaxies, which contain little dark matter, the new assembled object would inherit that deficiency. It would be a galaxy born from the debris of a crash, lacking the dark matter skeleton of its ancestors. This mystery cuts to the core of our understanding. If dark matter is not always tied to galaxies, it forces us to reconsider how galaxies form and evolve. It provides a unique test, a natural experiment. By studying these oddballs, we can learn what a galaxy behaves like when it is built from stars alone, giving us a clearer picture of what dark matter actually does in normal galaxies. The existence of even one such galaxy does not disprove dark matter, but it complicates the story beautifully, reminding us that the universe always has exceptions to its own rules, cosmic outliers that challenge our most cherished pillars of thought. The absence of a dark matter skeleton is a structural mystery, but sometimes a star's own light tells a story we cannot decipher. In the constellation Cygnus, over 1,000 light-years away, a seemingly ordinary star named KIC 8462852 began behaving in a way that defied every textbook. Its strangeness was first spotted not by a professional astronomer, but by the keen eyes of citizen scientists, volunteers sifting through data from NASA's Kepler Space Telescope. They flagged it for its bizarre light curve, the graph of its brightness over time. While most planet-hunting stars show gentle, periodic dips when an orbiting world passes in front, this star's light told a different tale. It displayed dramatic, irregular plunges in brightness. One dip blocked a staggering 22% of the star's light. For comparison, a Jupiter-sized planet would block only about 1%. Another series of dips created a chaotic, jagged pattern, as if something enormous and misshapen was drifting erratically across the star's face. This was not the signature of a clean, spherical planet. It was the fingerprint of chaos. The star soon earned a more memorable name, Tabbys-star, after the lead scientist Tabby, who brought it to global attention, and its mystery captured the world's imagination. What could possibly cause such extreme and irregular dimming? The initial natural explanation pointed to a vast swarm of comets. If a family of icy bodies, surrounded by enormous clouds of dust and debris, passed in front of the star, they could create the jagged, deep dimming patterns observed. But the scale required was immense, a swarm of hundreds of thousands of giant comets, a scenario that seemed statistically improbable. This is when the most thrilling hypothesis emerged from the realm of science fiction. Could we be witnessing an alien megastructure, specifically a concept proposed by physicist Freeman Dyson known as a Dyson sphere, a vast array of solar collectors built by a Type II civilization to harness the entire energy output of its star? A partially constructed swarm of such collectors with irregular shapes and orbits could perfectly explain the bizarre, non-repeating light dips. The idea was not that astronomers believed it was likely, but that they could not immediately rule it out. The star became a focal point for every major telescope on Earth and in space. Follow-up observations, particularly with the Spitzer Space Telescope and the Las Cumbres Observatory Network, sought a crucial clue: the dimming's dependence on wavelength. If the occulting objects were solid like planet-sized panels or asteroids, they would block all colors of light equally. If they were made of diffused dust, however, they would block more blue light than red. The data came in clearly. The dimming was much more pronounced in blue light than in red. This strongly favored a natural explanation: a cloud of fine dust particles smaller than grains of sand, likely from disintegrating comets or planetary collisions. Yet even this answer is incomplete. The source of that immense variable dust cloud remains unknown. Why is there so much of it? What process is generating it continuously to cause new dips years later? The full story of Tabbys-star is still unwritten. It stands as a monument to scientific curiosity, a reminder that when we look closely enough, even a single point of light can hold a universe of questions, pushing us to consider every possibility, from the dusty tales of dying comets to the faint, imagined glint of a civilization engineering its sun. The chemical story of the cosmos begins with a glaring inconsistency, a missing ingredient from the universe's first recipe. In the hot, dense furnace of the Big Bang's first few minutes, a process called Big Bang nucleosynthesis forged the lightest elements. Hydrogen and helium, the fuel for all future stars, were cooked in abundance, and their observed amounts today match the theoretical predictions with stunning precision. But for the third lightest element, lithium, the numbers do not add up. Our best models of that primordial inferno tell us the infant universe should have been seeded with about 3 times more lithium-7, its most common stable isotope. than we actually find. The oldest stars in our galaxy, which form from nearly pristine early material, act as cosmic time capsules. When we analyze their atmospheres, their lithium levels are consistently and bafflingly low. This is the lithium problem, a quiet but profound crack in our understanding of the universe's first moments. How could an element simply go missing on a cosmic scale? One leading theory looks to the stars themselves as the culprits. Perhaps this primordial lithium is not missing, but hidden or destroyed. As old stars churn over billions of years, their internal material can mix, dragging surface lithium down into hotter interior layers where it is fused into heavier elements and destroyed. If this mixing is more efficient than our current stellar models predict, it could explain the low observed levels. We will be looking at stars that have already digested their original lithium supply. Yet this solution is not entirely satisfying. Some of the oldest, most metal-poor stars show very little mixing and should preserve that primordial lithium like a fossil. Even in these stars, the lithium deficit persists, suggesting the problem might originate earlier. This points us back to the Big Bang itself. Could unknown physics during those first chaotic minutes have altered the lithium yield? Perhaps exotic particles, relics from an even earlier epoch, interacted with the primordial soup and altered the nuclear reactions that built lithium. Or maybe our understanding of the nuclear cross-sections, the probabilities of those early particle collisions, contains a subtle error. The discrepancy, while significant, involves a tiny amount of material relative to hydrogen and helium, making it a fiendishly difficult measurement to pin down in both theory and observation. It is a puzzle of precision, where being 99% right still leaves a fundamental question. The implications are monumental. Big Bang nucleosynthesis is one of the three great pillars of evidence for the Big Bang theory, alongside the cosmic microwave background and the expansion of the universe. For it to have a persistent, unexplained flaw is unsettling. Solving the lithium problem could force us to revise our models of stellar interiors, revealing new dynamics in how stars evolve. More dramatically, it might point to new particles or forces active in the universe's first seconds, a hidden chapter in physics that played out before the first star ever ignited. This missing lithium is a ghost from the dawn of time, a faint signature that our story of creation, for all its success, is still missing a crucial line. If the primordial elements are a flawed recipe, the universe's first light may carry an even deeper signature of something strange. This mystery has earned a dramatic and ominous name, the axis of evil. It refers to a bizarre and frankly unsettling pattern found in the most sacred map in all of cosmology, the cosmic microwave background. This faint glow is the cooled remnant of the Big Bang's fireball, a snapshot of the universe when it was just 380,000 years old. According to our foundational principles, this radiation should be the very picture of randomness. Tiny temperature variations, hotter and colder spots, should be scattered across the sky like a cosmic fingerprint, with no preferred direction or alignment. The universe on the largest scales should look the same in every direction, an idea called the cosmological principle. Yet when scientists created exquisitely detailed maps from satellites like Oumuamua and Planck, they noticed something that should not be there. Certain large-scale patterns in the temperature fluctuations appear to be aligned or correlated with the plane of our own solar system. It is as if the echo of creation itself knows which way Earth is tilted. Visually, if you take a map of the Symbi and draw a line along the ecliptic, the plane in which the planets orbit our sun, some of the largest warm and cool patches seem to line up along that axis. Even more strangely, the alignment also seems to relate to the equinoxes, the points marking Earth's seasons. This is profoundly troubling. The cosmic microwave background comes from a time long before our solar system, or even our galaxy, existed. Its patterns should have no knowledge of our local celestial geometry. It would be like finding a fossil from a billion-year-old sea creature that somehow contains a perfect sketch of the continent you are standing on. The implications are so counter to our standard model that scientists half-jokingly called it the axis of evil, because if it is real, it undermines a core pillar of modern cosmology. So is it real? The debate is fierce. Many argue it is a statistical fluke. When you analyze a map with millions of data points, you can sometimes find seemingly significant patterns purely by chance. It is the cosmic equivalent of seeing faces in clouds. Given enough clouds, you will eventually see one that looks eerily familiar. Others have searched meticulously for a systematic error, some subtle contamination from within our own galaxy or even from the instruments themselves. Perhaps dust in our solar system or the way the spacecraft scanned the sky introduced a faint signal that mimics this alignment. To date, no single convincing source of error has been identified that fully erases the signal. If it is not a fluke and not an error, then we are left with truly radical possibilities. One idea ventures into the realm of cosmic topology. Could the universe be finite and shaped in an unexpected way like a hall of mirrors? If space is connected in a complex topology, light could wrap around, creating patterns and correlations that make one specific direction look special from our vantage point. Another, even more mind-bending suggestion is that this alignment is a fossil from a time before the Big Bang, a scar from an earlier phase of the cosmos that imprinted itself on the newborn universe. The axis of evil remains an open wound in our understanding. It is a whisper that the universe might not be as isotropic and simple as we hoped, that our place within it or the nature of its birth might hold a privileged direction we do not yet comprehend. Every new, more precise map of the ancient sky is scrutinized for this pattern, a search for either the mistake that will let us rest easy or the confirmation that will force us to redraw the cosmos from its very beginning. Saturn's North Pole is crowned by a geometric marvel. This is the Great Hexagon, a six-sided jet stream of clouds that has whirled in perfect symmetry for at least 4 decades. When the Voyager probes first glimpsed it in the 1980s, scientists were stunned, suspecting an optical illusion or a temporary fluke. But when the Cassini spacecraft arrived years later, the hexagon was still there, a persistent and breathtaking feature etched into the planet's atmosphere. Its scale is almost incomprehensible. Each side of the hexagon is longer than the diameter of Earth, and the entire structure is so vast you could fit nearly 4 of our planets inside its boundaries. This is not a static shape painted on the clouds, but a roaring river of wind, a jet stream screaming along the hexagonal path at speeds over 200 miles per hour. How can nature, which so often favors curves and chaos, produce and maintain such a precise geometric form on a planetary scale? The search for an answer begins not in space, but in a laboratory. Physicists studying fluid dynamics can create similar shapes by spinning a cylinder of liquid. When the fluid inside rotates at a different speed than the container, the shear between the layers can generate stable, polygonal patterns in the flow. On Saturn, the container is the planet's deep atmosphere, and the rotating fluid is the weather layer. The hexagon appears to be a standing wave, a pattern pinned to Saturn's North Pole, likely generated by differences in the speed of deeper atmospheric currents. It is a kind of planetary scale vibration made visible by clouds, yet the laboratory experiments only deepen the mystery. While they can produce hexagons and other polygons, these shapes are often fleeting, changing or dissolving as conditions shift. Saturn's hexagon, by contrast, has shown a stubborn permanence. It has endured through seasons that last for years, through countless storms, and through the continuous churn of a giant planet's atmosphere. This stability is the true puzzle. What locks this wave in place so rigidly? The answer may lie in the unseen depths. Saturn is a gas giant with no solid surface, but it likely has a dense, rotating core. The interaction between this deep interior and the outer atmospheric layers could be providing the anchor, setting up a resonant cavity that sustains the hexagonal pattern for generations. It is a beautiful demonstration of how simple physical principles, writ large on a planetary canvas, can create art of staggering precision. The hexagon is a cosmic logo, a natural emblem for a world of fluid majesty, reminding us that even in our own celestial neighborhood, the most familiar laws of physics can still produce wonders we are only beginning to decode. While Saturn's hexagon is a fixed wonder, our solar system was recently visited by a traveler that refused to stay. In October of 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at impossible speed. They named it Oumuamua, a Hawaiian term for scout or messenger from the distant past. This was no ordinary asteroid from our own backyard. Its hyperbolic trajectory and blistering velocity revealed the stunning truth. Oumuamua was the first confirmed object from another star system ever seen passing through our solar system. It was a cosmic messenger, and it was profoundly strange. First, there was its shape, By analyzing how its brightness changed dramatically as it tumbled, scientists deduced it was not round, but extraordinarily elongated. The best fit was a pancake or a cigar-shaped object with a length up to 10 times its width. Nothing in our solar system looks quite like that. Then, there was what it lacked. As it sped past the sun, most astronomers expected it to behave like a comet. When a comet's icy surface is heated, it vents gas and dust, forming a glowing halo called a coma and often a tail. Oumuamua had no coma, no tail. It showed no visible outgassing at all, appearing as a bare, dark rock. Yet its motion told a different story. Precise tracking revealed Oumuamua was not just being pulled by gravity. It was also experiencing a slight but definite non-gravitational acceleration, a gentle push away from the sun. For a comet, this is common, caused by jetting material acting like a tiny thruster. But Oumuamua showed no signs of such jets, so what was pushing it? This is where the mystery exploded. The most famous and controversial hypothesis came from Harvard astronomer Avi Loeb. He suggested the acceleration could be explained by solar radiation pressure, the physical push of sunlight itself. For that to work on such a small object, Oumuamua would need to be extremely thin and light, like a sail. Loeb proposed it could be a discarded light sail, a piece of ancient alien technology drifting between the stars. The idea captured global imagination, framing Oumuamua as a potential artifact from a civilization long gone. The scientific community largely favored natural explanations, but nature had to be equally creative. One compelling theory proposed Oumuamua was a hydrogen iceberg. In the cold, dense cores of molecular clouds, solid hydrogen could form. A chunk breaking off would be invisible as it outgassed, explaining the acceleration without a visible coma, and would slowly erode away in interstellar space. Another idea suggested it was a fragment of solid nitrogen, sheared off the surface of a Pluto-like world in a distant solar system. The nitrogen would sublimate in sunlight, providing the push, and its reflective properties could match some of the observations. The frustrating, beautiful truth is that we will likely never know for sure. Oumuamua is already gone, racing out of our solar system faster than our probes could ever hope to catch it. It is now a faint speck receding into the void, taking its secrets with it. Its brief visit was a tantalizing glimpse, a single note from an interstellar symphony we are only just beginning to hear. It proved our cosmic neighborhood is not empty, that the galaxy is constantly tossing strange stones across our path. The next one might already be on its way, and next time, we intend to be ready. The strange visitor from another star challenged our ideas of what is out there, but a far more profound challenge lies in the ultimate cosmic destroyers themselves. This is the black hole information paradox, a conflict so deep it pits the two most successful theories in physics against each other. On one side stands Einstein's general relativity, which describes gravity as the curvature of space-time. On the other stands quantum mechanics, the rules governing the subatomic world. For decades they worked in separate domains, but at the edge of a black hole, they collide. The paradox begins with a simple quantum rule, the principle of unitarity. This states that information is never truly lost. If you could track every single particle in a burning book, in theory, you could reverse the process and reconstruct the book from its smoke and ashes. The information about its pages, its words, is always preserved, just scrambled. Now introduce a black hole. According to classical relativity, if you throw that book into a black hole, it is gone forever. The book crosses the event horizon, the point of no return, and is crushed into the singularity. The information it contained is erased from our universe, violating the sacred quantum rule. But Stephen Hawking added a devastating twist. He showed that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they slowly leak radiation. This Hawking radiation is thermal, meaning it is random heat, carrying no specific information about what fell in. Over unimaginable eons, a black hole will evaporate, radiating away all its mass until it vanishes in a final pop. And here is the paradox: if the black hole disappears and all that is left is this featureless thermal radiation, what happened to the information from the book? It seems to be permanently erased from reality. This is not just a bookkeeping error for physicists, it is a crisis. If information can be lost, then the entire logical framework of quantum mechanics, which underpins all chemistry and matter, breaks down. The universe would be fundamentally unpredictable. To resolve this, physicists have proposed mind-bending solutions. One of the most prominent is the holographic principle. Imagine the information about everything that falls into the black hole. The book, a spaceship, an entire star is not lost inside. Instead, it is smeared and encoded in 2 dimensions on the event horizon, like a cosmic hologram. The 3-dimensional object is gone, but a perfect 2-dimensional representation of it remains etched on the surface. When Hawking radiation escapes, it is not random. It slowly reads and carries away this encoded information, pixel by pixel, over the black hole's lifetime. The information is preserved, just in a form we cannot yet decipher. Another radical idea is the firewall hypothesis. This suggests that the event horizon is not a smooth gateway, but a searing wall of high-energy particles. The moment an object touches it, it is incinerated. The information from the object is immediately converted into energy and radiated away, never actually entering the black hole. This preserves information but violates Einstein's principle that crossing the horizon should be uneventful, leading to a new conflict. These are not abstract debates. Experiments are being devised to test them. Scientists are studying the quantum properties of simulated event horizons in labs, and they scrutinize the precise way black holes merge, searching for echoes in gravitational waves that might betray a firewall or a holographic surface. The resolution will rewrite our understanding of space, time, and information itself. It asks whether the 3-dimensional world we experience is just a projection, and what truly happens at the edge of the impossible. Centuries-old star charts hold a clue to a modern astronomical crime scene. In the late summer of 1181, court astronomers in China and Japan looked up and saw a new light in the constellation Cassiopeia. They called it a guest star, a temporary visitor that burned as brightly as Saturn for a full 6 months before fading from view. This meticulous record, preserved on silk and paper, is one of only a handful of reliable supernova sightings in human history. For modern astronomers, it is a tantalizing cold case with a precise date and location. The challenge is to find the corpse. When a massive star explodes as a supernova, it leaves behind a rapidly spinning neutron star called a pulsar, often embedded in an expanding cloud of debris. The search for the remnant of the 1181 supernova seemed to find a perfect match in an object known as 3C58. This is a nebula of tangled filaments with a powerful pulsar, J0205 plus 6449, spinning at the heart of it. The pulsar is a dynamo, one of the brightest known in radio waves, and its estimated age appeared to align beautifully with the 8th-century-old event. The case looked closed, a neat piece of cosmic forensics connecting an ancient observation to a modern discovery, but upon closer inspection, the evidence began to unravel. The first problem is the pulsar spin. By measuring how quickly its rotation is slowing down, astronomers can estimate its age. For pulsar J0205, that age comes out to about 5,000 years, far older than the 8th century since the guest star appeared. It is possible the pulsar was born spinning much faster, which would skew the age calculation, but the discrepancy is significant. The second, more damning clue is the remnant itself. Supernova remnants expand at tremendous speeds, thousands of kilometers per second. When scientists measured the expansion of 3C58, they found it was crawling. Its current velocity suggests an age of several thousand years, not several hundred. It is as if detectives found a car at the scene of a recent hit and run, but the engine is cold and the tires are flat from decades of disuse. This object seems too old to be the product of the 1181 explosion, so if 3C58 is not the remnant, what is? The search continues, and it leads to another fascinating structure known as the monogem ring. This is a vast, faint bubble of soft X-ray emission in the constellation Gemini, possibly the shell of an ancient supernova. Its estimated distance and size could place its explosion around the right time frame to match the guest star. Could the monogem ring be the true faded ghost of that medieval spectacle? The puzzle deepens because the ring is enormous and diffuse, making it hard to pinpoint a central source like a pulsar. We might be looking at the hollowed-out shell of the explosion, while the pulsar itself, the dense core of the dead star, has rocketed away into the dark, leaving no trace. This is a detective story where the witness testimony is impeccable, but the physical evidence refuses to cooperate. The ancient astronomers gave us a time and a place. Our technology has found promising suspects, but their alibis do not quite hold. The solution may require a missing piece, a faster, younger pulsar hurtling unseen through interstellar space, or a reinterpretation of the clues we already have. Every time we look at the quiet patch of sky where the guest star once blazed, we are seeing it through the eyes of an astronomer from 8 centuries past, both of us searching for the same answer in the silent dark. Our universe is built on a familiar cast of characters, particles like electrons and quarks that follow well-understood rules. But what if there is an entire hidden sector of reality made of something that does not behave like matter at all? This is the speculative realm of unparticles, a theoretical concept born from the frontier of particle physics. The name itself hints at the strangeness. Unparticles are not particles in any normal sense. They are proposed to be scale-invariant stuff. In our everyday world, scale matters. A planet behaves differently than a grain of sand, but something that is scale-invariant looks the same no matter how closely you zoom in or out. A classic natural example is a coastline. Its jagged complexity repeats at every magnification. Unparticles would possess this fractal-like property, a blurry fractional existence that defies the neat whole number dimensions of ordinary mass and energy. They would not have a specific mass like an electron, but something physicists call fractional mass dimensions, making them appear as a continuous spectrum rather than discrete particles. The idea emerged from attempts to explain certain high-energy physics anomalies, tiny discrepancies between prediction and experiment that could be the first cracks in our standard model. Unparticles are theorized to be the lingering influence of a hidden sector, a parallel realm of forces and fields that interacts with our own universe only through gravity or the faintest of touches. This makes them potential ghosts in the machine, capable of influencing phenomena we can barely measure. One tantalizing possibility is their effect on ghostly particles called neutrinos. Neutrinos are shapeshifters, oscillating between different types as they travel. Unparticles could provide a subtle new force that alters this oscillation pattern in detectable ways, a hidden hand tweaking the behavior of the universe's most elusive particles. Even more dramatically, unparticles could leave an imprint on the ripples of spacetime itself, gravitational waves, the specific ringing of 2 black holes merging, or the subtle polarization of the cosmic microwave background could carry signatures of this scale-invariant stuff interfering with gravity in ways Einstein never anticipated. While still highly theoretical, bordering on mathematical speculation, the concept of unparticles represents a thrilling direction of thought. When our most powerful colliders find nothing but confirmation of known physics, theorists must venture into the wilderness of ideas, proposing entities that sound like science fiction to explain the silence. Unparticles are a placeholder for the unknown, a symbol of the next great mystery that might be hiding just beyond our current reach. They remind us that the fundamental ingredients of reality may be far stranger than particles and forces, waiting to be discovered in the subtle fractional spaces between what we think we know. The universe's ancient light holds more than just a controversial axis. It also contains a profound and chilling emptiness. This is the mystery of the cold spot in the cosmic microwave background. When scientists created their exquisite maps of the Big Bang's afterglow, they expected a sky peppered with small, random temperature variations. Instead, they found a region in the constellation Eridanus that is not just cold, it is shockingly, improbably cold. This patch of sky is far larger and colder than our best models of cosmic inflation can comfortably explain. It is a cosmic bruise, a blemish on the face of creation that refuses to fade. The statistics are stark. The probability of such an extreme feature arising by pure chance in a standard universe is less than 2%. This forces a difficult question: is our entire model of the universe's infancy wrong, or have we stumbled upon something even stranger? One compelling and deeply unsettling explanation reaches beyond our single universe. This is the multiverse hypothesis. The theory of cosmic inflation suggests our universe is just one bubble in a frothing sea of eternally expanding space, with other bubble universes constantly budding off. What if in the unimaginably dense early moments our infant universe grazed another? That colossal collision, a bump between 2 separate realities, could have left a scar, a region where energy was drained away, imprinting a cold spot on our cosmic microwave background. It is a breathtaking idea, the cold spot as a fossilized kiss from another cosmos, yet a more conventional answer might lie closer to home, or at least along the line of sight. Imagine the light from the Big Bang traveling for over 13 billion years to reach us. If on its long journey it passed through an immense region of space that was mostly empty, a cosmic supervoid, that passage could have drained its energy. This is due to an effect called the integrated Sachs-Wolf effect. As light enters a large underdense region, it climbs out of a gravitational well that is becoming shallower due to dark energy's influence. This double loss of energy saps the photons, making them appear colder when they finally arrive. It is like a marathon runner hitting a long uphill stretch at the very end of the race, arriving completely drained. The search for this proposed supervoid has yielded mixed results. Astronomers have indeed found a large, sparse region in the general direction of the cold spot, but its size and emptiness may not be sufficient to fully explain the dramatic temperature drop. The void we have found might be a coincidence, or perhaps we have not mapped its full, tenuous extent. The debate is a beautiful example of scientific tension. Is the cause a local structure, a vast emptiness within our universe, or is it a fundamental crack in our cosmology, a signature of a greater multiverse? Each answer carries profound weight. A confirmed supervoid would challenge our understanding of how such immense structures form, revealing a lumpiness in the cosmos we did not predict. Evidence of a multiverse collision will be the most monumental discovery in human history, proving we are not alone in the grandest sense possible, that our entire reality is just one island in an infinite archipelago of universes. For now, the cold spot simply hangs in the data, a quiet, persistent chill. It is a reminder that our most successful theory of the universe's birth still has room for the extraordinary, a blank space on the map that could be a mere shadow or the outline of a door to everything else. That persistent chill in the ancient sky speaks to a universe that is not what it seems, and the evidence for that hidden reality is written in the very motion of the stars themselves. This brings us to one of the most direct and elegant mysteries, the strange way galaxies spin. Look at a majestic spiral galaxy like our own Milky Way, a vast pinwheel of stars and gas. You might expect it to rotate like our solar system, where planets closer to the sun orbit much faster than those farther out. Mercury zips around in a matter of weeks, while Pluto takes centuries. This is how gravity works with a concentrated central mass. The stars in a galaxy, if held only by the gravity of the visible stars and gas we can see, should behave the same way. Stars near the crowded center should orbit quickly, while those out in the sparse galactic suburbs should drift along at a leisurely pace. But when astronomers in the 1970s like Vera Rubin and Kent Ford actually measured these orbital speeds, they found something that shattered that expectation. The stars out at the very edges of spiral galaxies were not slowing down. They were orbiting just as fast as the stars closer to the center. The rotation curve, the graph plotting orbital speed against distance from the galactic core, did not fall off. It stayed flat, extending far beyond the visible edge of the starlight. This was not just a small discrepancy, it was a fundamental breakdown of the predicted physics. Imagine spinning a bucket on a rope. The bucket is a star, the rope is gravity. Now imagine you could make the rope longer and longer, but the bucket never slowed its spin. You will be forced to conclude there must be more rope, an invisible length you cannot see, providing the necessary tension. For galaxies, that invisible tension is the gravitational pull of dark matter. The flat rotation curve was the first major, undeniable clue that we were missing most of the universe's mass. It told us that galaxies are embedded within vast spherical halos of something that does not emit or absorb light, something whose gravity alone holds these fast-moving stars in their tracks. But what if the rope itself is different? A minority of scientists propose an alternative, that we do not need invisible matter, but rather a tweak to the laws of gravity itself. This idea is called modified Newtonian dynamics, or MOND. It suggests that gravity behaves differently at extremely low accelerations, like those experienced by stars in the faint outskirts of a galaxy. Under MOND, the familiar Newtonian equations get a small modification that becomes significant only when gravitational forces are incredibly weak. With this single adjustment, the theory can reproduce flat rotation curves without invoking any dark matter at all. It is an elegant solution that appeals to the desire to explain observations without filling the cosmos with ghosts. Yet for all its appeal, MOND faces severe challenges. While it works well for explaining the rotation of individual galaxies, it struggles to account for all the other evidence we have for dark matter's existence. It has a difficult time explaining the bullet cluster, where two galaxy clusters collided. Observations show that the mass, mapped by gravitational lensing, is separated from the visible gas. This suggests the mass is in a form that does not interact with anything, even other dark matter, exactly as predicted by particle dark matter, but posing a serious problem for a modified gravity theory. Furthermore, the detailed structure of the cosmic microwave background, the precise way galaxies cluster on the largest scales, and the very formation of galaxies in the early universe all point toward a universe dominated by a cold, collisionless dark matter component. Most cosmologists see dark matter as the simpler, more comprehensive framework, even if we have not yet detected the particle itself, so the rotation of galaxies remains a pivotal mystery. It is the clean observational anchor for a cosmic component we cannot see, a ghostly signature written in the speed of stars. Whether the final answer is a new particle or a new law of physics, this simple graph of orbital velocity is the stark line where our comfortable understanding ended and the true hidden depth of the cosmos began. The rotation of galaxies is a puzzle of motion, but time itself is the silent river that carries all motion forward. What is time? We feel its passage in every heartbeat and every sunset, yet in the equations of physics it becomes something profoundly strange. Einstein taught us that time is not a universal clock ticking the same for everyone, but a flexible dimension woven together with the three dimensions of space into a single fabric called space-time. Gravity slows time and speed stretches it, yet this mathematical treatment does not capture why time feels so different from space. We can move left or right in space, but we are dragged helplessly forward in time. This one-way direction is known as the arrow of time, and its origin may be the most fundamental mystery of all. The most compelling explanation points to a concept called entropy, which is a measure of disorder or randomness in a system. The universe, from its incredibly ordered, low-entropy state at the Big Bang, has been evolving toward higher and higher entropy ever since. Think of a drop of ink in a glass of water. It starts concentrated, then slowly diffuses until it is evenly spread throughout. This process is irreversible. The universe is like that ink drop spreading out. Our perception of past and future is tied to this cosmic gradient of increasing disorder. We remember the past because it was a more ordered state, and we cannot remember the future because it is statistically more disordered. Every time you break an egg, you are witnessing the arrow of time in action. You never see a splattered egg reassemble itself in the pan, because that would mean entropy decreasing, which is overwhelmingly improbable. But this leads to a deeper, more unsettling question. Is time itself a fundamental ingredient of the universe, or is it something that emerges from a more basic, timeless reality? At the deepest levels of quantum gravity, where the fabric of space-time is thought to dissolve into a quantum foam, our familiar notion of time may vanish entirely. One stark example comes from the Wheeler-DeWitt equation, a foundational attempt to combine general relativity with quantum mechanics. In this equation, time simply does not appear. The universe it describes as static, frozen. All moments from the Big Bang to the distant future would exist simultaneously in a block, like frames in a film strip. Our lived experience of flowing from one frame to the next would then be an illusion, a story our conscious minds tell themselves as they move through this eternal structure. If true, this means the river of time is not a river at all, but a vast, unchanging landscape, and we are simply hiking a trail through it, mistaking our journey for the land itself. This is not just abstract philosophy, it underpins all of cosmology. Understanding whether time is fundamental or emergent is crucial for making sense of the Big Bang, the nature of black holes, and the ultimate fate of everything. Our entire experience of reality, of cause and effect, of memory and anticipation, hangs on the answer to this single profound question. Our experience of time's flow is a mystery, but at the smallest scales, reality itself seems to wait for our attention before deciding what it is. This is the quantum measurement problem, a riddle so bizarre it challenges the very meaning of existence. In the quantum world, Particles like electrons do not have definite properties until we look at them. An electron can be spinning both up and down at the same time, existing in a blend of possibilities called a superposition. It is only when we perform a measurement, when we observe it, that this fuzzy cloud of potential collapses into a single, definite fact. The electron chooses a state. This raises a devastatingly simple question: what counts as a measurement? Where is the line between the quantum blur and the solid world we experience? Is it the act of a conscious mind observing the result? This idea that consciousness causes the collapse is haunting and profound, suggesting our awareness is not just a passive receiver, but an active participant in shaping reality. Most physicists find this unsettling, as it places human thought outside the laws of physics. The more mainstream explanation points to a process called decoherence. Imagine a perfectly still pond representing a quantum particle in superposition. Now toss a single grain of sand into it. Ripples spread out, interacting with the water. That interaction is like the particle bumping into even a single photon or air molecule in its environment. Decoherence argues that the quantum system never truly collapses. It just becomes hopelessly entangled with the countless particles around it. The information about its original superposition leaks out into the universe, becoming so scrambled and dispersed that it is for all practical purposes gone. The particle appears to have chosen a state because we, as large, messy collections of particles ourselves, are only able to see the one outcome we became entangled with. But if decoherence explains why we see a definite world, it does not eliminate the deeper mystery of where all the other possibilities go. This leads to the most radical interpretation of all, the many worlds theory. It proposes that there is no collapse at all. Every time a quantum system faces a choice, the entire universe splits. In one branch, you see the electron spin up. In another, an identical version of you sees it spin down. Both outcomes are equally real, playing out in parallel, non-communicating universes. Every possible outcome of every quantum event actually happens, creating a mind-numbing multiverse of branching timelines. This is not science fiction. It is a serious, if controversial, attempt to preserve the pure mathematics of quantum mechanics without adding a special rule for measurement. The implications stretch far beyond the lab. If the many worlds view is correct, then the origin of our universe from a quantum fluctuation is not a singular miracle, but one possibility in an infinite tapestry. It suggests that every conceivable history and future is real somewhere. The quantum measurement problem is not a minor technicality. It is a direct confrontation with the nature of reality. Are we living in one single concrete timeline, or are we just one thread in a fabric of infinite possibilities, unaware of the other versions of ourselves reading these same words in a slightly different way? The answer, if we can ever find it, will tell us what the universe truly is when no one is looking. That quantum blur of possibilities settled into a world of solid matter, but our very existence depends on a single, miraculous imbalance. The universe should be empty. According to our best theories, the Big Bang should have created matter and antimatter in perfectly equal amounts. These are mirror opposites, identical in mass but opposite in charge. When a particle of matter meets its antimatter counterpart, they annihilate in a flash of pure energy, leaving nothing behind. If the cosmos had begun with perfect symmetry, every proton should have met an antiproton, every electron an anti-electron, in a total, catastrophic cancellation. The end result would be a universe filled with nothing but light, a silent expanse of photons with no stars, no planets, and certainly no one to wonder about them. Yet here we are living in a cosmos made almost entirely of matter. Every atom in your body, every star in the sky, is evidence that the scales were tipped. Something in the universe's first fleeting moments broke the symmetry and favored matter over antimatter. This is the Baryon asymmetry problem, and it asks perhaps the most fundamental question of all: why is there something rather than nothing? The search for an answer leads us to the work of physicist Andrei Sakharov. He outlined 3 necessary conditions that must have been met for matter to win. First, there must be a process that violates what physicists call charge parity symmetry, or CP violation. This is a subtle difference in the behavior of particles and antiparticles. In a perfectly symmetric universe, if you swapped every particle for its antiparticle and viewed the scene in a mirror, physics would look exactly the same. CP violation means it would not. The mirror image would be slightly off. This tiny bias could have allowed matter to be produced just a fraction more often than antimatter. We have actually observed CP violation in the lab, in the decay of certain exotic particles called kaons and bemesons, but the amount we have seen is far, far too small to account for the overwhelming dominance of matter we see in the cosmos. The second condition is a violation of baryon number. Baryons are particles like protons and neutrons, the building blocks of atomic nuclei. In everyday physics, the total number of baryons is conserved. You cannot just create a proton from nothing. But in the extreme energy of the early universe, this rule must have been broken, allowing a net production of matter over antimatter. The third condition is a departure from thermal equilibrium. The universe had to be out of balance, changing rapidly, so that the processes creating the asymmetry could not simply reverse themselves as things cooled down. Think of it like a sudden frost. If you cool a supersaturated solution quickly, crystals form and are locked in place. If you cool it slowly, everything just settles back into a uniform liquid. The early universe needed that rapid change to freeze in the matter excess. The hunt is now on to find a process that satisfies all three of Sakharov's conditions with enough power to explain our reality. Particle accelerators like the Large Hadron Collider are smashing protons together at near light speed, searching for new particles or interactions that could have tipped the scales. Neutrinos, those ghostly particles that barely interact with anything, are also prime suspects. If neutrinos are their own antiparticles, a property called Majorana particles, they could have triggered a process called leptogenesis in the early universe, creating an asymmetry in leptons like electrons that later transformed into the baryon asymmetry we see today. Experiments deep underground are trying to catch neutrinos in the act of this rare transformation. This is not just abstract curiosity. The fact that you are here to listen, that Earth exists, that the night sky is dotted with stars instead of being uniformly dark, is the direct result of this ancient, imbalanced event. We are the product of a cosmic accident, a 1 in a billion fluke that left just enough matter behind to build everything we know. Solving this mystery means uncovering the very reason we are here at all, a signature from the first second of time that decided something would remain. The matter that survived that ancient annihilation now faces a far slower but equally inevitable destiny. Our universe is not static. It is a story with an ending we are only beginning to read. The final chapter hinges on a single invisible actor, dark energy, and the precise nature of its relentless push. Will the cosmos end in fire, ice, or something far more violent? The first and perhaps most haunting possibility is the big freeze or heat death. In this scenario, dark energy continues to accelerate the expansion at a steady, gentle pace. Galaxies beyond our local group will first redden, then fade from view as their light is stretched beyond detection. Within each surviving island universe, star formation will eventually cease as the raw gas is locked away in dead stars or expelled into the void. The last stars, small red dwarfs, will burn for trillions of years before finally sputtering out. Black holes will slowly evaporate via Hawking radiation over timescales so vast they make the current age of the universe seem like a blink. The end state is a universe uniformly cold, dark, and empty, a dilute sea of photons and elementary particles so far apart they never interact again. It is the ultimate triumph of entropy, a silent, eternal equilibrium. But dark energy may not be so gentle. What if its repulsive force grows stronger over time? This leads to the truly apocalyptic finale known as the Big Rip. If dark energy's equation of state, labeled by the parameter W, is less than -1, its density would increase as the universe expands. This phantom energy would eventually overpower every force that holds things together. First, galaxy clusters will be torn apart, then individual galaxies. As the end nears, stars will be ripped from their orbits. In the final minutes, planets will be shredded from their suns. In the last terrifying moments, atoms themselves will be pulled apart, nuclei separated from electrons, and finally, space-time itself might be fractured. The universe would end not with a whimper, but with a catastrophic fundamental disintegration. The third classic ending offers a cyclical rebirth, the Big Crunch. This requires dark energy to weaken or reverse, allowing gravity to finally win the cosmic tug-of-war. The expansion would slow, halt, and then reverse. Galaxies will begin rushing toward each other, the sky heating up as background radiation is blue-shifted. The universe would collapse back into a hot, dense state mirroring the Big Bang, potentially triggering a new expansion, a new universe in an endless cycle of death and rebirth. So which fate awaits us? The answer lies in two numbers, the critical density and dark energy's equation of state. The critical density is the precise amount of matter and energy needed to just barely halt the universe's expansion, balancing it on a knife edge between eternal growth and eventual collapse. Measurements of the cosmic microwave background and large-scale structure tell us our universe's total density is incredibly close to this critical value, but the composition is the shock. It is dominated by dark energy. The key is W. If W equals exactly -1, dark energy is a constant, leading to the big freeze. If W is less than -1, we get the big rip. Current observations from supernova, the CMB and baryon acoustic oscillations all pin W very close to -1, consistent with a cosmological constant. For now, the data favors the long, cold freeze, but the uncertainties are still significant. A slight deviation in future, more precise measurements could tilt the forecast from a slow fade to a violent end. This is not just abstract cosmology, it is the ultimate fate of every structure, every memory, every bit of information that ever was. It asks whether our universe is a one-time event fading into oblivion or part of an eternal, breathing cycle. The answer is written in the accelerating flight of the galaxies, a message in the dark we are still learning to decode. The ultimate fate of our universe is a lonely one, but what if our cosmos is not the only story being told? The idea of a multiverse suggests our entire universe, with all its galaxies, laws, and history, is just one bubble in an infinite, frothing sea of other realities. This is not science fiction, but a serious, if controversial, extension of our best theories of physics. It arises from two powerful ideas, eternal inflation and the string theory landscape. Imagine the Big Bang not as a single explosion, but as a never-ending chain reaction. The theory of eternal inflation proposes that the rapid expansion of space-time that created our universe never truly stops. Instead, it continues eternally in a background sea of hyperinflated space. In this roiling quantum foam, new bubble universes are constantly budding off, each with its own Big Bang, its own random set of physical constants, and its own destiny. Our universe is simply one such bubble that stopped inflating locally, allowing matter and stars to form. Meanwhile, beyond our cosmic horizon, an infinity of other bubbles are being born, each potentially with different laws of physics. String theory, a candidate for a theory of everything, adds another layer to this picture. It suggests that the fundamental constants of nature, like the strength of gravity or the mass of an electron, are not predetermined, but are set by the way extra dimensions of space are curled up and stabilized. The theory predicts a vast landscape of possible stable configurations, perhaps 10 to the 500 different versions. Each version corresponds to a universe with a different set of physical laws. In the multiverse framework, every possible configuration in this landscape is realized somewhere in some bubble. This leads to a staggering conclusion: every conceivable universe where life is possible and every inconceivable one where it is not actually exists. But does this count as science? The central criticism is testability. If other universes are permanently beyond our causal horizon, forever disconnected from us by inflating space, how can we ever gather evidence? Proponents argue that while we may never visit another universe, we might detect its ghostly signature in our own. One thrilling possibility is a cosmic bruise on the oldest light we see. If our infant bubble universe collided or grazed another bubble in the multiverse during its early inflation, that colossal impact would have sent shockwaves through the fabric of space-time. Those ripples could have left an imprint, a distinctive pattern of circular asymmetries or cold spots in the cosmic microwave background. Some scientists point to the famous unexplained cold spot in the CMB as a potential candidate for such a collision scar, a fossilized kiss from another reality. The multiverse forces a profound philosophical shift. It recontextualizes the miraculous fine-tuning of our universe, the fact that dozens of physical constants are perfectly balanced to allow for atoms, stars, and life. In a single universe, this fine-tuning seems like an unbelievable coincidence, perhaps requiring a designer. But in an infinite multiverse where every possible set of constants exists, it is no longer a miracle, it is a statistical inevitability. We find ourselves in a universe that can support us simply because we could not exist anywhere else. This is the anthropic principle applied on a cosmic scale. Whether a legitimate frontier of physics or untestable metaphysics, the multiverse idea expands our imagination to its breaking point. It suggests that all stories are true somewhere, that every choice branches into a new reality, and that our entire existence might be a single page in an infinite library of realities, most of which are utterly alien and forever unseen. We have journeyed to the edge of the multiverse, but every story must have a first page. This brings us to the final and greatest cosmic mystery. We call it the Big Bang, the moment our universe began its expansion from an unimaginably hot, dense state some 13.8 billion years ago. Yet this name is a profound misdirection. The theory of the Big Bang describes what happened immediately after the beginning, not the beginning itself. It tells us the universe expanded and cooled, forming particles, atoms, and eventually galaxies, but it says nothing about what caused that expansion to start in the first place. What or who lit the fuse at the very origin? Our physics breaks down completely. We can trace the cosmic timeline back to a fleeting moment called the Planck time, just 10 to the negative 43 seconds after the moment of creation. Before this point, the universe was so incredibly small and dense that the effects of gravity become as strong as quantum effects. Our two great theories, general relativity and quantum mechanics, which have guided us so far, become incompatible, producing meaningless infinities. It is like having a map that perfectly details every continent but becomes a blur of scribbles at the exact point labeled "you are here." To peer beyond this veil, we must venture into the realm of theoretical physics, where ideas are our only tools. One of the most profound ideas suggests that the universe came from literally nothing, not empty space but a true void, the absence of space, time, and matter. According to quantum mechanics, empty space is not truly empty. It's seized with virtual particles that pop in and out of existence on borrowed energy. Could the entire universe be the result of a quantum fluctuation on the grandest possible scale, a single, stable bubble of space-time that simply appeared? In this view, the total energy of the universe might still be zero, with the positive energy of all matter and radiation perfectly balanced by the negative gravitational energy of space-time itself. Our entire existence will be a cosmic free lunch, a fluctuation that simply never smoothed back out. A second, equally mind-bending possibility is that our Big Bang was not a beginning, but a transition. This is the concept of a cyclic or bouncing universe. Imagine a previous cosmos that expanded, then eventually contracted under its own gravity in a big crunch. Instead of collapsing to a point of infinite density, perhaps it rebounded, like a ball compressed to its limit and then bouncing back. Our expanding universe will then be just the latest cycle in an eternal series of expansions and contractions, with each bounce resetting the cosmic clock. There will be no true beginning, only an endless breathing rhythm of creation and destruction. A third spectacular idea connects the birth of our universe to the death of a star in another reality. Could our universe have been born from a black hole in a parent universe? When a massive star collapses into a black hole, it forms a singularity, a point of infinite density where our laws of physics cease. Some theories suggest that the extreme conditions inside a black hole singularity could trigger the birth of a new separate spacetime, a baby universe branching off from its parent. In this cosmic genealogy, every black hole in our universe could be a portal to a new cosmos with its own laws and dimensions. We will be living inside the offspring of an alien star's catastrophic death. These are not just wild guesses, but extensions of our most advanced mathematics, attempts to sketch a map where none exists, yet they all ultimately bring us to the same precipice, the frontier where science meets philosophy and pure wonder. We are asking the question that may have no answer we can comprehend, because the concepts of cause and effect, of before and after, may themselves be born in that first instant. To ask what happened before the Big Bang might be like asking what is north of the North Pole. The question itself may lose all meaning. This is the ultimate horizon of human knowledge. Every mystery we have explored, from dark matter to the nature of time, finds its roots in this first unknowable moment. The search for the answer is not just about our past, but about the fundamental nature of reality. It forces us to confront the possibility that some truths are forever beyond our reach, locked behind the veil of the Planck time, and yet we keep looking, building ever more powerful particle colliders to recreate the conditions of the early universe, and designing space telescopes to read the faintest whispers from the dawn of time. We're driven by a need to know our own origin story, to understand why there is a here and a now at all. In that search at the very limit of understanding, we do not find an end, but a beginning of a different kind, the start of a deeper, more humbling curiosity. This voyage through 25 cosmic enigmas has taken us from the familiar orbits of our own solar system to the very edge of reality itself. We have stood before the silent paradox of an empty galaxy, felt the ghostly pull of unseen matter, and witnessed the ancient light of creation holding patterns we cannot explain. Each mystery, from the hexagon on Saturn to the whisper of the wow signal, is a testament not to a failure of science, but to its greatest triumph, its boundless curiosity. These puzzles are the engines of discovery, the open doors that beckon us forward. Every unanswered question is an invitation to look deeper, to think more boldly, and to build the tools that will one day turn confusion into understanding. The universe, as we have seen, is far stranger and more magnificent than we could have ever dreamed. It is a living story, and we are both its readers and its authors, writing new chapters with every observation, every experiment, every gaze into the starry dark. The next great revelation, the solution to one of these profound puzzles, could be waiting just around the corner, in the data from a new telescope or the spark of an idea in a curious mind. Which of these cosmic mysteries captures your imagination the most? Let us know in the comments below, and if you are hungry for more journeys to the edge of understanding, be sure to subscribe. Our exploration of the cosmos has only just